Welcome, my name is Thyra. In this video, we are going to design an isolated footing subjected to axial load. We'll be using the Eurocode. Therefore, if you see any formula that is not being referenced, it is certainly from the Eurocode. Let's get started. Isolated footings are shallow foundations which consist of a pad or slab that supports a single column. Like any other foundation, their primary role is to transfer loads from the superstructure to the ground. They are the most commonly used footings because they are economical and simple to construct. Now let's talk about the footing we'll be designing in this video. The footing consists of a pad with unknown dimensions. The pad supports a centrically loaded column with a section size of 300 by 300 millimeters. The column is subjected to two types of gravity loads: a characteristic permanent load of 900 kilonewton and a characteristic variable load of 400 kilonewton. The main material used for the footing is of course concrete with a characteristic compressive strength of 30 megapascal. The concrete is reinforced with rebars of characteristic yield strength equals to 500 megapascal. The safe or allowable bearing capacity of the ground or soil is given to be equals to 200 kilonewton per millimeter squared. These are the data we're going to use to dimension our footing to make sure it can support the given characteristic load without failing. Now that we know more about the footing we'll be designing, let us look at the design steps we'll be following. First, we will determine the design load at ultimate and serviceability limit state. Then, we will use the ultimate design load to determine the thickness and effective depth of the pad. After that, we will use the service design load to determine the breadth and length of the pad. Let us dive in and determine these unknowns. To determine the design load at ultimate and serviceability limit state, we proceed as follows. For ultimate limit state, the design axial load is given by this equation. When we substitute the characteristic permanent and variable loads, we obtain 1815 kilonewton. For service limit state, the design axial load is given by this equation. When we substitute the characteristic permanent and variable loads, we obtain 1300 kilonewton. As mentioned earlier, the ultimate limit state will be used to determine the thickness of pad, while the service limit state will be used to determine the size of pad, that is, the breadth and length of pad. To determine the thickness and effective depth of pad, we use this equation where C num is the nominal cover and phi s is the diameter of bars. To determine the nominal cover, it is recommended that when the pad rests on a blinding, the nominal cover should be greater than or equals to 50 millimeters. On the other hand, when the pad rests directly on the soil, that is, without blinding, the nominal cover should be greater than or equals to 75 millimeters. Here, we will assume the pad rests on a blinding. Therefore, the nominal cover will be taken as 50 millimeters. As for the diameter of bars, we will assume 20 millimeter bars. Substituting the nominal cover and the diameter of bars into this equation, we are left with the effective depth as the only unknown that will enable us to determine the thickness of pad. To determine the effective depth, we use the equation of shear stress at the face of the column. In this equation, beta is equals to 1 when no eccentricity of loading exists. U0 is the perimeter of the column and it is equals to 4 times 300. NED is the ultimate design load which we found to be equals to 1815 kilonewton. Substituting these values and rearranging the equation, we get effective depth equals to this. Now you can see that the only element preventing us from getting the effective depth is the design shear stress at the face of the column. We will assume the design shear stress to be equals to half the maximum allowable shear resistance. The maximum allowable shear resistance is given by this equation, where V1 is the strength reduction factor and FCD is the design compressive strength. We use the computed values of the strength reduction factor and the design compressive strength to obtain the maximum allowable shear resistance. We then substitute this value here to obtain the value of the assumed design shear stress at the column face. Now, substitute this value here to obtain the effective depth equals to 573 millimeters. Substituting this value into our original equation, we get a pad thickness of 643 millimeters. We'll use a pad thickness of 650 millimeters, from which we get our new effective depth equals to 580 millimeters. So far, we've determined the ultimate design load and the service design load. Then, we've used the ultimate design load to determine the thickness and effective depth of pad. Now, we are going to use the service design load to determine the breadth and length of pad. To determine the breadth and length of pad, we are going to equate the allowable bearing capacity of the soil to the service design load plus the self-weight of pad divided by the area of pad. The allowable bearing capacity was given to be equals to 200 kilonewton per millimeter squared. And we have determined the service design load to be equals to 1300 kilonewton. When we substitute these values into the equation, we are left with two unknowns, the weight and area of pad. The weight of pad is given by this equation, where h is the thickness of pad, which we found to be equals to 650 millimeters. Gamma c is the unit weight of concrete, which we will take as 25 kilonewton per meters cube, and AF is the area of pad. When we substitute these values into the equation, we get 16.25 AF. We then substitute this value here, and we are left with AF as the only unknown. When we solve for AF, we get AF equals to 7.075 meters squared. Say we are designing a square pad or footing of size B equals to L. The area of pad will be equals to B squared. Solving for B, we get B equals to L equals to 2.66 meters. We will use B equals to L equals to 2.7 meters, which gives us an area of 7.29 meters squared. Here we are at the end of the first part of our isolated footing design. We've determined the ultimate design load from the characteristic permanent and variable loads. We've then used it to determine the thickness and effective depth of pad. We've also determined the service design load and used it to determine the breadth and length of pad. Thanks for watching till the end. Please like, comment, and subscribe. Whether you like this video or not, please comment it. I want to know what you think to improve future videos. In the next video, that is part 2, we shall talk about bending moment reinforcement. Again, thanks for watching. I wish you well.